Okay, so I just wanted to briefly talk about section 12.9, changes of variables in multiple integrals. So basically, um, what section 12.9 discusses is essentially using substitution for a double or a triple integral. You know how to do substitution for a single integral, but what if you needed to do or wanted to do a substitution for a double integral? Well, anytime you do a substitution, you're effectively changing the integral with respect to one variable with respect to an integral with respect to another variable. And that effectively is basically changing how the area under the curve looks, because you're also changing the curve as well. And when you deal with double integrals, you're dealing with regions of integration. So you can have, for instance, like they show in figure 1 here, you can have a region S with respect to variables u and v, and through certain transformation, you can convert that region S to a region R with respect to x and y. Now, I don't want to get, I want to just sort of get right generally to the point we need to get to here. But if you were to do a change of variables in a double integral, okay, so you have a double integral over some region R with variables x and y, and maybe I'll highlight this. And you can't do that double integral for some reason. The integrand won't work. You could let x equal a function of u and v and y equal a function of u and v, and the double integral will change to an integral not with respect to variables x and y, but with respect to variables u and v. And there is a adjustment to the double integral. So naturally, x gets replaced with its function of u and v in the function, and y gets replaced with its function of u and v in the function. But then you also have a what's called a Jacobian adjustment. That's what that looks like, an absolute value with the two partials, the partial of x and y over partial of u and v. That stands for a Jacobian. And that's the adjustment that needs to be done. Now, when you do a substitution with respect to one variable, you're actually doing a Jacobian as well. You just didn't realize it, but it's just a 1-by-1 Jacobian. Well, it's a Jacobian that's the adjustment when you do the substitution. Usually there's a constant, that gets involved when you go from one variable to another variable. In the new integrand, there's a constant, It's the same for a double integral. And the Jacobian, hold on here, I just got to find it where they define it. The definition of a Jacobian is given here. And this is something that you will very likely see in other classes. I don't know if anybody of you has seen a Jacobian before, but it's the determinant, 2-by-2 determinant, where the entries of the 2-by-2 determinant are those partial derivatives. Okay, so that is what a Jacobian is. And it is involved when you do a change of variable with respect to a double integral. And incidentally, I'll just mention this while I'm at it. Hold on. I might have to go. Yeah, triple integrals. You can also make a change of variable. You can let x be a function of u, v, and w, y be a function of u, v, and w, and z be a function of u, v, and w. And then the new transformed integral has that new function with respect to u, v, and w times that Jacobian, and then du, dv, dw. So it's a fairly involved process. And I want to just show one example here where let me see here, one example. It was actually example 3, and I'm not going to go into it in huge detail. You can certainly look it over on your own if you want. But in this problem, just got to find it. Yeah. So they want you to evaluate this double integral where the integrand is e to the power x plus y divided by x minus y, where R is the trapezoidal region. That's your region R. There's no way you can get that the antiderivative for like the whether you're doing dx dy or dy dx. You're not going to be able to get an antiderivative with that integrand, with that exponential integrand, where you have e to the power x plus y over x minus y. So it's easier what you do is you make a change of variables. And the natural change of variables would be let u equal x plus y and let v equal x minus y. That would be the natural change of variables. But if you make that change of variables, then you have to adjust your region R. You have to transform the region R. Okay, so in figure 8, the region R is this trapezoidal region given in the second picture. It's a trapezoidal region bounded by the vertices 1, 0, 2, 0, 0, negative 2, and 0, negative 1. Well, if u equals x plus y and v equals x minus y, all of those, the four sides of that region get transformed into the four sides of that region S that you see in the orange region S, and that's your new region D. Okay, so when you do a substitution, it's going to naturally change your region D because your region D, or your region R, I should say, it's going to change the region R because region R is with respect to variables x and y. Region S is with respect to these new variables u and v. And so when you get this newly transformed region S, now basically you compute the Jacobian. Okay, so let me see here. I think I can highlight this. Trying to make sure it all shows. So one moment. Yeah, I can probably do that. That's fine. So based on what x and y are, the Jacobian, all the Jacobians are equal. All the entries are equal. Well, you have a half, half on the first row, and a half, negative a half on the second row. You take the determinant of that. I'm sure you've. Let me just go to the whiteboard here. I'm sure you've seen before that if you have the determinant of a 2 by 2, okay, it's going to equal A times D minus B times C. How many have seen that before, maybe in a class, for a 2 by 2 determinant? Maybe you learned it in an earlier class. Well, nobody's ever done a determinant of a 2 by 2. All right, Noreen has seen that. Okay. If you take linear algebra, you'll certainly learn a lot about determinants. Incidentally, I'm teaching that class this fall. I'm teaching that class, so feel free to join me. All right, let me go back to the thing there. So in this case, you would have for that determinant, you'd have 1/2 times negative a half, which is a negative fourth, minus 1/2 times 1/2, which is minus a fourth. So that minus a fourth is negative 1/2. And then they talk about how they they change the region R. They look at the four sides of the region R and convert them to these four sides of the region S. Okay, it's just basically transforming the images based on that x is equal to a half times u plus v and y equals a half times u minus v. And so what happens is, again, you get this new trapezoidal region, okay, and in figure 8, and you can see that if you're going to integrate with respect to u first, which you would want to do, you're in figure 8, your function on the left is u equals negative v, your function on the right is u equals positive v, and the limits are going to go, the v limits are going to go from 1 to 2. Okay, and so what happens is then, when you do that, this is your new double integral. And that is an integral that can be done, that can be integrated. And you end up getting an answer. So it's really a very lovely approach to do double integrals and triple integrals. This substitution concept is very nice. But of course, it only works in certain instances. And a lot of times now, with technology, what engineers do is when they have a difficult integral like this to compute, a difficult double integral, they might just use technology like MATLAB to get an approximation of the answer, which is, the true answer is 3/4 times parentheses e minus e to the negative first power. That is the best answer in the world, in the universe, right? A computer can estimate that. And so, these techniques were developed a long time ago, and naturally back then, there weren't advanced computers to find these double integrals. So the techniques were developed, and that got mathematicians the answers they need. But of course, to apply this technique, as you can see for the double integral, and then suppose you even add a triple integral, it's quite a bit of work. So, but at least you see you have been exposed to section 12.9, change in variables and multiple integrals. And should you see this someday, you are at least familiar. You can say, hey, I remember Dr. Diddy talking about this. All right, are there any questions? Incidentally, I had to use this in graduate school for, I think there was like maybe one or two homework problems in one of my stat classes that I had to use this for. So it's possible you could see it. And okay, great. Well, I will stop the recording then. Very good.